We were all taught in school that the world is made of stuff, of matter, of mass, of atoms. Atoms make up molecules, molecules make up materials, and everything is made of that. But atoms actually are mostly empty. For example, if this ball were the nucleus of an atom, a proton in a hydrogen atom, for example, then the electron circling this, which would describe the outer limits of that atom, would be out by that mountain over there, roughly 20 miles away. And everything in between is empty. In fact, the universe is mostly empty.
Within all the atoms and molecules, all the space within them, the particles take up an insignificant amount of the volume of an atom.
Dr. William Tiller said, "Within all the atoms and molecules, all the space within them, the particles take up an insignificant amount of the volume of an atom." But it's the particles that supposedly make up matter, so scientists focus on them in their experiments. And as the research continued, scientists discovered that the very small particles they were finding did not behave as they were supposed to. Basically, Newtonian physics only worked well on large objects, objects we can see with our naked eyes, but not on a subatomic level. This was the beginning of quantum physics, and the most famous experiment that got everyone opening their minds to new possibilities about the universe and how it works is called the double-slit experiment. Let's make sure we understand this double-slit experiment so far. When we shoot matter, like a BB or a marble, at a barrier with two slits, we get two bright streaks on the screen behind in line with the slits, like this. And when we shoot waves, like waves of water, through a barrier with two slits, one wave becomes two waves on the other side of the barrier, and when two waves hit, they interfere with each other. If the top of one wave aligns with the top of another wave, it's called constructive interference, and the result is a new and bigger wave. But if the top of one wave aligns with the bottom of another wave, it's called destructive interference, and the result is that they cancel each other out, and there's no wave at all. And when constructive and destructive interference happen together, you get an interference pattern on the back screen that looks like this. Now, if we shoot an electron, which we have always thought of as a particle, a little piece of matter, through a barrier with two slits, you would think we would get a pattern on the back screen that particles make, like this. But we don't. Instead, we get an interference pattern that waves make, like this. The conclusion is that electrons, which are the building blocks of what we call reality, are not solid particles at all, but exist as waves as well. In this wave form, they are called quanta, which is why the study of how they behave is called quantum physics. But that's not the end of the double-slit experiment. Let's rejoin Captain Quantum where he...
Electron is very peculiar in the sense that when you are not looking, electron can be here, can be there, or can be over there in the corner of this room. It can be all over this room, so to speak. But whenever we look, this is the strange thing about these electrons. Whenever we look, we always find them to be in one particular Geiger counter, although we may have a room full of Geiger counters. We never hear the Geiger counter sticking all over the room. This is the fundamentally important stuff about the electrons.
It was here that physicists stepped forever into the strange, never-world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? the observer collapsed the wave function simply by observing.
Particles are really what they seem to be. They're momentary manifestations, momentary poppings of this deeper imaginary realm, this wave-like realm, this implicate order, as David Bohm would say it, this quantum wavy function, as quantum physicists might talk about it, in which there is no particle. There's just this waviness which can spontaneously pop out as particle.
Once again, let's make sure we understand, because this is so important. As we said earlier, when we shoot an electron toward a barrier with two slits, without watching what it does at the barrier, we get an interference pattern like this. But when we watch or measure what happens at the barrier, the electron becomes a particle again, and makes a particle pattern on the screen behind, like this. In physics, this is called the measurement problem, because the nature of an electron changes when you look at it or try to measure it. It collapses from being a wave into a particle in a specific location in space and time, which is what we see as reality. This is called collapsing the wave function. Remember that term, collapsing the wave function, because we'll talk more about it later. This means that an electron, the core element of what we call our solid physical reality, is only a solid particle, is only matter when someone is looking at it. Otherwise, it's a wave and not solid at all. In his book, The Holographic Universe, Michael Talbot said, "There is compelling evidence that the only time quanta, or electrons, ever manifest as particles is when we are looking at them. When an electron isn't being looked at, it is always a wave." To put it the other way around, the natural state of an electron is as a wave. It only pops out of its wave state to form a particle in a specific location in space and time when it is being observed. Then, when it's not being observed, it goes back into its wave state. But it turns out that it's not just the electrons that pop in and out of existence. Listen to Dr. Jeffrey Satinover.
Matter is not what we have long thought it to be. To the scientist, matter has always been thought of as sort of the ultimate in that which is static and predictable. We like to think of space as empty and matter as solid. But in fact, there is essentially nothing to matter whatsoever. It's completely insubstantial. Take a look at an atom. We think of it as a kind of hard ball. Then we say, oh, well, no, not really. It's this little tiny point of really dense matter right at the center, surrounded by a kind of fluffy probability cloud of electrons popping in and out of existence. But then it turns out that that's not even right. Even the nucleus, which we think of as so dense, pops in and out of existence just as readily as the electrons do.
Dr. Satinover said, even the nucleus of an atom, which we think of as so dense, pops in and out of existence just as readily as the electrons do. So it is not only the electrons that exist as waves and then pop into a specific location in space and time when they are observed, but also the nucleus. And the most recent research has even found that whole atoms and molecules do the same thing. Physicist Nick Herbert says this means that the world behind our back, where we are not looking and cannot observe, is always a radically ambiguous and ceaselessly flowing quantum soup. But whenever we turn around and try to see the soup, our glance instantly freezes it and turns it back into reality. Herbert believes this makes us all a little like Midas, the legendary king who never knew the feel of silk or the caress of a human hand, because everything he touched turned to gold. Likewise, we can never really know the true nature of the quantum universe, because every time we try to observe it, it turns into matter. Richard Feynman, a physics professor at the California Institute of Technology, is reported to have said that if you really understand this double-slit experiment, you can understand all of quantum physics. You will hear me say fairly often that one of the best clues or hints about how our universe actually works can be found in our kids' video games. Right now, take a short look at a game called Minecraft.